Okay, so let's start seeing some examples. I'm going to compute a line integral. Whoops, I'm in pencil mode. I want to compute a line integral of this vector field on that curve. All right, now you'll notice the curve is parametrized, and that does kind of sort of suggest maybe the Chapter 5 plug and chug, and sometimes that's what you got to do, sometimes. But let's not throw in the towel just yet. Let's hope that something nice will work out. Right? So let's figure out, first of all, where are we in the diagram? Reminder, here's the diagram. Our vector field, you'll notice, has 3 components. Our curve has 3 coordinates in the parameterization. We are in R3. We're looking for a line integral in R3, and so we are here. So these are our candidate theorems. Divergence theorem's off the table. There shall be no triple integrals in this discussion. Right? Let's see, going back here. Now, okay, so what do we do? Oh, diagram. What should I do? Well, I'm looking at a vector field of which I'm computing a line integral. I should compute the curl. Right? I'm just following the instructions of what the diagram tells me to do. Yeah, take this vector field, compute the curl, and you get 0. So the consequences of this are, because I get 0, there is an anti-gradient. I can use the fundamental theorem of line integrals. And I can also use path independence if I want to, but let's call that plan B. I mean, if fundamental theorem of line integrals works out reasonably, then it's kind of easier, right? Okay. But let's consider our other options before we, just jump right in. Let's also ask, this curve, given that I'm looking at a line integral, is the curve that I'm given a boundary? Said differently, is there an anti-boundary surface, in which case I can consider using Stokes' curl theorem? Well, how are we going to decide if a curve is a boundary? Let's think about the geometry. Closed curves are typically boundaries. And curves that are not closed, starts over here, ends way over here, that's just not going to be a boundary of a surface. Boundaries close up. That makes sense. So let's look at our parameterization, and if you plug in t equals 0 and look at x of 0, and then if you look at t equals 1, plug that into the same parameterization, you get x of 1, and these 2 points are not the same. So it's not closed, and it's not a boundary. And so Stokes' theorem is off the table. There is no anti-boundary surface. Yeah, everybody good? Now, it's very important to make this realization. Let me show you what students step on a landmine very often in these kinds of problems. Students not thinking about this might say, oh, look, the curl is 0. Oh, okay, whoa, then the line integral, we're interested in the line integral of f dot dx. Okay, well then I'm just going to do surface integral curl f dot ds. Oh, the curl was already shown to be 0, and so therefore I get 0. Happy face. And this is a terrible landmine, because nothing that's written on the page is both true and relevant to the actual solution to the question. I guess arguably the student did correctly compute that the curl was 0, and that might be worth a teeny tiny little bit. But the suggestion that this line integral is a flux of something is absolute nonsense. It's just not true. Did everybody see the problem? So this is very, very dangerous. Be super careful. Don't get sloppy with your domains. I mean, notice the big gaping hole here. I did not indicate a domain for this flux integral. If you want to use a boundary theorem that goes to the right, therefore claiming that you have an anti-boundary for your original domain, you better make sure there really is one. Otherwise, you step on this landmine and you get, something in the vicinity of 0 points on that question. there any questions about this? Is everybody happy? Does everybody understand the problem and the solution? Okay, so yeah. So that is very dangerous. Okay, so can't use Stokes' theorem. Fine, no worries. We can use fundamental theorem of line integrals. Let's just proceed with that. I need to find the anti-gradient, and this is just a matter of details, really. So I'm going to let y'all fill in the blanks on this. This vector field does have an anti-gradient. It's a couple of anti-partials. You play a game with constant function, partial constant functions. Find the anti-gradient. F of b minus f of a, that whole game. Okay. Let's see the next example. Another line integral. So line integral in R3. I wanted to be in highlighter mode. Line integral in R3. 1, 2, 3 components. By the way, let's look at this vector field real quick. Now I know y'all are looking at the same stuff that I'm looking at here, so I can't. I'm going to pose this as a question, as if you can't see the answer right there in front of you in the book. Okay, but quick, compute the curl. You can do it. Come on, what is it? What's the curl? Curl is 0. I claim it's obvious that the curl is 0. There's a simple reason why. Notice that the first component of this vector field is all x's. The second component is all y's, and the third component is all z's. So when you start taking various partials, what are you going to be taking the partial of this with respect to? Well, at some point you'll be taking its y partial, that's 0. At some point you'll be taking its z partial, also 0. This, at some point, you'll be taking its x partial, obviously 0. At some point, you'll be taking its z partial, obviously 0, right? You're always taking, in some sense, kind of cross partials. And so if the first component is all x's, second component is all y's, third component is all z's, the curl is obviously 0. And, how often this comes up? Oh, maybe not a lot, but it's a nice little time saver, little quick trick to, keep in your back of your mind, always be on the lookout for. Kind of leaps off the page that this structure is there. And it's just nice to save yourself a calculation to know that curl is always 0. Okay, anyway, that was just a little side quickie. Curl is 0. Okay, the curl is 0. That means that in our line integral in R3, because the curl is 0, there is an anti-gradient. Fundamental theorem of line integrals is on the table. Good deal. We're not going to have to plug and chug this one. Okay. Okay, right, but what about Stokes' theorem? It's a possibility. Well, we got to look and see if this curve is closed or not. Plug in t equals 0. Out comes x of 0. Plug in t equals, plug in t equals 1. Out comes x of 1. And this time, those points, same point. This curve, wacky though it is, starts and ends at the same point. That's a closed curve. And I have to acknowledge that I don't know exactly what that curve looks like. But we could explore the possibility that this is, in fact, a boundary of a surface, and we could, go down that road. Now, between the two, I'd rather use fundamental theorem of line integrals, right? It's going to be real hard for me to figure out what this surface looks like. How am I going to parameterize that surface if I use Stokes' curl theorem? It's just that doesn't look like it'd be so easy. But the fundamental theorem of line integrals we know it's usually easy. Okay. All right. But something nasty happens on your way to the fundamental theorem of line integrals as well, though. Notice I'm going to have to take the antipartials. I'm going to need to take an x antipartial of that. I'm going to have to use integration by parts twice. I don't really like that. I'm going to have to take a y partial of this. It's a little annoying. I'm going to have to take a z partial of that. That's actually intractable. I can't take the z antipartial of that. So we kind of do have a problem here. Both of the theorems apply, but both of them are not particularly convenient, or so it seems. Everybody see where we're at? Okay, so it turns out there's another nice fact that I'm not going to prove, and you may not cite the following result on a Math 212 test, but I want you to be aware that it's true. If, in considering one of these integrals, the theorem on the left applies, and the theorem on the right applies, both of them, you get to choose either one. Useful trick. The answer is 0. And let me show you by example how this works out. Let's look at this example that we're looking at here. Yeah, I don't know how to find this little f. Right, finding the anti-gradient, it's got brutal integrals in it, right? But I do know that the fundamental theorem of line integrals tells me that it's f of b minus f of a. Oh, wait a second. A and b are the same point. So this f of b minus f of a is arguably f of a minus f of a, and I don't really care what f is. F of a minus f of a is 0. Everybody see how that worked? So there's that 0. Okay. You can argue the other way on this if you're so inclined. You could say, well, look, this anti-boundary, oh my gosh, I don't know what that looks like, in fact. I mean, our curve is outrageous. The surface is going to be kind of outrageous too, I would imagine. So exactly what the nature of this flux is, man, I don't know. That's going to be an ugly surface, but the curl is 0. And ugly though it may be, this surface does exist. All right? This is not one of those landmine situations where the surface doesn't exist. So I am in fact taking a flux of 0, and I get 0. As of course I certainly better, because we already know the answer is 0. So anyway, it's kind of a neat thing to keep in mind. So I encourage you to just remember this as a just for sanity check purposes. If you find yourself with, hey, I can go either way with this, you do have to pick one, and you do have to give me one or the other of the two arguments that I just showed you. I want to see one of those arguments, but you get to know in advance that I know my answer had better be 0, and so just make sure that you do get 0. If you don't get 0, you know you messed up. Everybody on board? That's kind of cool. Okay. Alrighty. Moving along. So, here's another line integral. This again is a line integral in R3, you'll notice. And so, so again, we are here. We need to compute the curl. To consider if I can use that theorem, I'll need to think about possible anti-boundary surfaces to think if I can use that theorem. Okay. Well, this vector field, compute the curl, not 0. Now, right away, I know what that means. I know right away because, according to the diagram, right, looking at this line integral, I took the curl, I got not 0. That means that there is no anti-gradient. I cannot use the fundamental theorem of line integrals. So don't bother trying to find an anti-gradient. It's not there. Everybody on board? Okay. So can we use Stokes' curl theorem? We next wonder. Well, I got to think about my curve. My curve is the intersection of that plane and that cylinder, and we have a picture here. And we've considered this sort of scenario before: a cylinder intersecting with a plane, and we get a sort of a tilted ellipse like this. And now let's think about orientations real quick. The question states that this curve is oriented counterclockwise as seen from above. And looking at this, going the wrong way with it. Looking at this picture, counterclockwise as seen from above. means like that. Looking from up there, that's counterclockwise. Is everybody happy? Okay. All right. Is this a boundary of something? Why, yes, it is. That is a boundary of that surface, among others. But again, do yourself a favor. Pick the easy surfaces. Right? Okay. So one thing we can do, we could use Stokes' curl theorem. Using Stokes' curl theorem, I don't know why. Okay. Yeah. So fine. Okay. So there is a anti-boundary surface. We can use this theorem. I've already got the curl already computed. I just need to figure out how am I going to deal with this resulting flux integral. I have to do a flux now over this yellow surface. We could hope for a lucky break. We could hope that maybe this dot product be 0 or something, but it ends up being that it isn't. You look at the specifics of how this works out. Here's your curl vector. Here's your normal vector. Notice that the normal vector comes from the equation of the plane in this case. Right? And that dot product just isn't 0. Curl dot in, not 0. So it is a constant, and that's nice. But we are, in fact, going to end up with an actual surface integral that has to be computed. Is this a win? We could use Stokes' curl theorem. But to the question of whether it's a win, I don't think that's clear. Right? So we are going to have to compute the area of an elliptical surface as it turns. The constant integrand factors out. You still have to compute that area. I don't know how good that deal that is. Let's look back at the original problem. Our vector field, pretty nice, right? How do I parameterize this curve? That curve is actually pretty easy to parameterize. X and Y are just cosine and sine. And the X and Y on the actual curve that we're interested in are the same X's and Y's as on that projection, which is just, again, cosines and sines. What is Z? Well, this equation here, this equation is X plus Y plus Z equals 0. So what is Z? Z is negative X minus Y. So negative cosine t minus sine t. So it's just not that bad to parameterize and find X and Y and Z. It's not a bad parameterization. Again, the field that we're plugging into, not that bad. I think if it were me, I think I would go ahead and just chapter 5 this question. And not deal with the surface integral. But suit yourself. Either way will work just fine. One thing you might do is think about both of those options. So come back to this question at some later time and work out the line integral directly, chapter 5 style. See how that works out. Then go through and look at the Stokes' theorem surface integral. Work that out. Both of them are an integral. You're going to have to parameterize in both cases. In one case, you're parameterizing a curve. In one case, you're parameterizing a surface. And see which one you like better. Anyway, it's an interesting comparison. So the reason I like this example is I like to point out, these boundary theorems, these are not magic wands, right? These are tools. And sometimes they will turn a hard problem into an easy problem. Sometimes they will turn a medium problem into another medium problem. And, then it's not clear whether it's useful. Okay, on the other hand, what if I have that vector field, same vector field as before, and this time, plane, cylinder, but it's a different plane. Here we get lucky. There, the normal vector and the curl, I don't have the curl written down here, but the curl was -1, -1, -1. The normal vector and the curl are perpendicular. And so when I do this dot product, curl dot normal vector, you do get 0, and there Stokes' curl theorem is a big win, right? Turning the line integral into a flux integral, but it's a flux integral of 0, definitely preferable. Yes?
So if you ever think of how we find the curl dot s equals to a constant, do we still have to parameterize the domain?
Yeah, well, you have to... Yeah, it is the area, but it's the area of that surface, and the area of that surface is the ellipse. So here, I'll write it down in here. So Stokes' theorem would tell us that the line integral around this curve is the flux through this surface S of curl F dot n ds. Now you're quite right, that is a constant, and so that'll factor right out at just some value, right? But notice that you're left with the surface area of that surface. Yeah, and
it's cool that you can find the absolute min and the absolute max, and then you have your one axis.
Yeah. What? Yeah. Well, sure. If you want to go, that's fine. Yeah, you could totally do that, right? So you got to decide for yourself, though, is that easier or not as easy as just parameterizing the curve in the first place? And it's a kind of a toss up, but yeah, totally. Does that make sense? Okay. Everybody happy with the options? Alrighty. Okay, here's another line integral. We'll do a couple of flux integrals in a minute. Another line integral. This time, however, notice two components. So we are no longer in the R3 diagram. We are now up here in the R2 diagram looking at a line integral. So now our options are fundamental theorem of line integrals and Green's theorem, which we will arbitrate first by computing Green's operator. Right? Again, the diagram tells you exactly what to do. Right? So use the diagram. Okay, so we compute Green's operator, this vector field. Green's operator is 2, which is not 0. So we did not get 0. That there is no anti-gradient. We can't use the fundamental theorem of line integrals for this problem. Everybody happy? Okay, next question. What about Green's theorem? Let's see here. We've got our curve is the boundary of the unit square. Now, if we're going to use Green's theorem, I need for the boundary of the unit square to be the boundary of something. Is the boundary of the unit square the boundary of something? Well, yeah, it's right there in the language. Right? The boundary of the unit square is the boundary of the unit square. Right? So the way the question is stated kind of tells you what your two-dimensional region here. It's that solid unit square. Okay. So we can use Green's theorem, and we proceed. This is let's see here. This D is the unit square, and Green's operator, again, conveniently we've already computed Green's operator. It's 2. And so look at the easy little integral that falls into our lap. We're doing a double integral over the unit square of the constant value 2. And that's a super easy integral. The answer is 2. Yeah, everybody happy? Note how much easier this is than the alternative, that, the boundary of the unit square. If you were to, brute force this, you would have to parameterize 4 separate line segments, right? You'd have to do that, and then that, and then that, and then that, and it would be, neither one of those 4 chunks would be that bad, but still, I think this is easier. Okay, here we go, running out of time. Let's get this done. Here's a vector field given, and I want to compute a flux. Now, before we move on, I want to compute a flux through a surface. We are now over here. these are our two candidates. We're going to need to compute the divergence. Gradients and anti-gradients don't have anything to do with these questions, right? So don't give away your sort of unawareness of the context by writing gradient on your answer to one of these flux questions. It's just not relevant. Right? Likewise, f of b minus f of a. It's got nothing to do with anything for this question. Okay, so let's look back at our question with all that in mind. Here is, again, our vector field. I'm giving some free information here that this vector field is also the curl of this other vector field for whatever use you might want to make of that. Right? So what are we going to do about this? Let's compute the divergence. Oh, by the way, can anybody tell me the divergence instantly just by a casual inspection? Yeah, it's 0. That's right. Because it is a curl. And if you're looking at a curl of something, the divergence is 0 by this theorem down here. Right? Everybody happy? So, not only do we know that because the divergence is 0, there is a vector field that is the anti-curl. In fact, I actually know what that vector field is. I am given the anti-curl. The way this question was phrased, here it is. That's the anti-curl right there. Right? Everybody happy? Okay, all right. So now let's think about our surface. It's the part of the elliptical paraboloid with this equation so it's the part that is above the xy plane. Now, this is one of those cases we've talked about before. Don't be sloppy with the interpretation of what this surface is. Some students like to think in terms of, okay, I'm going to take this surface, but I want to think about the solid underneath that surface. I see this surface, I see the xy plane. I'm going to pretend we're talking about the solid between this surface and the xy plane. It's not what it says, right? But if you're thinking in terms of that solid, and then you say, oh, yeah, but I'm supposed to have a surface, so to make this square peg go into that round hole, I'm going to pretend that somewhere it says boundary of that solid. And students think that they've got this surface with a top part and a bottom part, which is just not what this says, right? Be very careful with this too. This can get you into tremendous trouble. This surface, very importantly, is just part of the elliptical paraboloid. That's it. It's just the bowl, right? It's the part of that paraboloid that's above the xy plane, so just a bowl. There is no sort of saran wrap, across the overturned sort of eating surface of the bowl. It's just the bowl. Okay. So just this. Alrighty. Now we've computed the divergence. The divergence was 0. So we can use Stokes' curl theorem. Stokes' curl theorem is on the table. Now, normally we don't know how to find anti-curls, but in this case, the anti-curl was given. So I know what that f is in this line integral. It's that given anti-curl. And following along with that, missed. My integral f was given as a curl of something. Therefore, I know that anti-curl, and therefore I know what is the integrand for my resulting line integral. And so this is the new line integral that Stokes' theorem tells us we can use instead. Everybody happy? By the way, this line integral turns out really nicely. This line integral is there's a line integral over that curve. It's line integral over this curve like this. That curve, you'll notice, is entirely in the xy plane. That means that everywhere you go around this curve, dz is always 0. After all, z is always 0, so dz is always 0. And that means that this dot product is always going to be 0. Everybody on board with that? So this integral is sort of, I'm going to say, immediately 0. And that'll bear out if you write out the details, but the integral is 0. Okay. All right, real quick, and then we'll get to TCEs. I do want to show you the alternative. Another thing you can do, keep in mind, whenever you have 0 in the operator, you could use the left boundary theorem, or you could use domain independence. Right, that's another option when the operator is 0. So divergence is 0 here, therefore surface independence on the table. And so looking back at this question, let's decide if surface independence is a good choice. Well, our surface was this. The boundary is that curve. Another surface with that same boundary is this surface. And that's a fantastic surface. It's flat, after all. Right? So I could just, say the magic word, surface independence, and just let's compute on that flat solid ellipse instead. And that's the calculation we have down here. The surface independence I change to my new surface. On my new surface, the normal vector is vertical. It's down, but nevertheless vertical. And so this flux integral has a dot product that's always 0, and therefore this integral also obviously 0. So you have a couple of pretty good options to choose from here. Stokes' curl theorem works out in this case because the anti-curl lucky break was given. Surface independence works out really great in this case as well. So take your pick. It's another sort of, whichever you prefer. Either of these is fine. Okay. Don't use Gauss's divergence theorem here. Gauss's divergence theorem does not apply because this surface is not a boundary of a solid. Again, it just isn't. The surface that we were given is this. It is open at the bottom. It's not a boundary. And if you use Gauss's divergence theorem and say, hey, the divergence is 0, let's do a triple integral of the divergence. Triple integral of 0 gives me 0. The argument is complete nonsense, and you stepped on the landmine. Everybody happy? Okay. All right. There's a couple more examples. This next one is easy read. We're looking at an obvious boundary. Flux through an obvious boundary, use the divergence theorem, and it works out nice. This last one, I'm going to let y'all read. Now, there's a lot of equations down there on the board, but it turns out that this one is also a pretty freebie kind of a question. You'll notice we're doing a triple integral of a divergence, and so we can immediately use Gauss's divergence theorem to reinterpret that as a flux. And it's a flux where another dot product turns out to be 0. So don't get lost with the algebra. Most of that algebra is camouflage. Right? This one works out just fine also. I'm going to let y'all read those. And we're out of time, and we are done with the book. So done with Math 212. Okay, let me stop the recording. We're going to do TCEs now.